Welcome back to the computational science program and the course on machine learning and computational physics. I just wanted to scroll down to the schedule which we have. And last time we actually started to look at the basics of neural networks and some of them mathematics and architecture. And you can find the slides on this link. And there's also a video of the lecture which we went through last week. This video will be uploaded for today's lecture, will be uploaded right after the lecture. The topic which I wanted to discuss today in more depth is the famous backpropagation algorithm. So we're going to derive that one, which is essentially the way by which we can update and find the optimal parameters for a neural network. But we are going to repeat some of the elements from last week, and then we are going to derive the backpropagation algorithm. And when we've done with the backpropagation algorithm, which essentially is an application of the chain rule, we're going to link this to an algorithm which is widely used in the calculations of derivatives, and it's called automatic differentiation, where you can, in principle, calculate the high-order derivatives or derivatives to a numerical precision without having to either evaluate them by finite difference schemes or using symbolic packages like Mathematica or symbolic Pythons, which normally end up with expressions which can be less efficient to implement numerically. So we are going to actually show the likeness, or actually the equality, between the backpropagation algorithm and something which is called reverse mode in automatic differentiation. And I will try to explain to you the basic details and why the backpropagation algorithm is more efficient than doing a forward derivation algorithm. So let's go immediately over to the whiteboard, because we will essentially stay with the whiteboard today because we need to do some of the mathematics here. So I'm going to switch over to that immediately. So let's go to the whiteboard and start reminding ourselves about some of the technicalities which we went through last week. So a neural network is a very important basic building stone in the theory of the deep learning methods. So let's try to repeat some of the things which we discussed. And we used an acronym for neural networks as NN. So if we look at the architecture, so I'm just going to repeat some of the things which we discussed last week. This defines the architecture of a neural network, defines what we would call the model, compared to what we had when we did linear regression, for instance, or logistic regression. In linear regression, we could have something like a polynomial approximation. So when we look at the architecture of a neural network, we would then define the so-called number of hidden layers, which we ended up defining during last week's lectures. Hidden layers. We would define the number of hidden nodes, or neurons as they're being called. And these are typically the number of hidden nodes in a specific layer. We would then have to define something which we call the activation function, which we're coming back to. So this will be part of the model. And we saw last time that we have many ways to define this activation function. So every node produces a specific output, and this output can then be modulated by a specific activation function. And one of the more famous ones, which was introduced in the very beginning of the field and is mimicking a way by which we can model how neurons fire, is a sigmoid function. We can have a tanh function. We had something which we defined last week, which is called the rectified linear unit. We can have the exponential linear unit, etc., etc. And there are many such functions. Then what we need to define next is another part of the neural network. So let's highlight this piece here first. So this will be the architecture itself for the model. And then we're going to have something which we define as the cost function. This is the way we assess whether the model which we have defined is a good one or not. This is the cost or loss function and the optimization part. So let's just quickly remind ourselves about what kind of ingredients enter here. And many people feel a little bit disappointed, as I mentioned last time, by all the parameters which are being introduced. And when you set up a neural network, you actually have to fine-tune many of these parameters in order to find the optimal score. So the type of cost or loss function is very important. A typical loss function, which we have seen, is a mean squared error. We need to think of a regularization. So this can be of the type of L1 or L2, as we have discussed earlier. So the most common ones are L1, an L1 norm or an L2 norm. The L2 norm led to linear regression, what we call ridge regression, whereas the L1 led to lasso regression. And then we have the gradient descent methods. Gradient descent, I just write that as a GD. And here we can have stochastic. Let me say stochastic. We can have parameters like number of batches, which you've been playing around with in project number 1. We need to define something like the learning rate, or what we also may call as the step size in the gradient calculation. We have parameters like epochs, etc. And then we have also different optimization schemes. And this could be schemes like ADAGRAD, ADAM, RMS-prop, and many other schemes. So the optimization choices are also things which we have to define here. Then we have other specifics. This could be something like pre-processing of the data, pre-training of the data. So suppose now you're going to model the output of an experiment in, let's say, particle physics, and then you have some tracks in a detector which are translated into images where you can see the tracks of the different particles, how they behave in a magnetic field. Then you could think of having trained a network beforehand on either optimization data based on numerical simulations. So you may have a theoretical model which allows you to generate data, and they can be used to pre-train a network, which then can be used to analyze a specific experiment. Alternatively, you have run the analysis of data from a previous experiment, and then you want to use this pre-trained network with another set of data. So we can have things, additional other specifics. Let's write that down. So we can have a pre-training and pre-processing. We can have the initialization of the network. This is actually an important issue, how you initialize your unknown parameters, which in this case are weights and biases. There's something which is called dropout. There are things which are called gradient cutting, because the gradient can actually blow up when we calculate the gradients. So there are many, many different techniques which are used to tune the training of a specific neural network. Now, one thing which we didn't discuss in detail last week is actually the universal approximation theorem, which I want to state here, which is an important theorem and which lets you understand why neural networks are so useful. So I just wanted to state the theorem here so that we have, we're not going to prove it, but I just want to state it so that you get a kind of feeling of what we are dealing with actually. So in approximation theories, you may have seen proofs for, let's say, a polynomial approximation to a given function. You may have heard of something like the Stone-Weierstrass theorem, which is used to prove that. You may have studied Fourier functions, where you approximate a given periodic function in terms of a set of sines and cosines. And there you can actually provide a precise error based on the approximation which you make. So the what we could think of now is that we have a continuous function, and we have the data set y, which is now defined in terms of a continuous deterministic function. And this function here lives in the unit cube of d dimensions between 0 and 1. It's a deterministic function, so we're assuming that this y is given by a deterministic function. Deterministic function, which we assume to be continuous. Assumed to be continuous, and it's defined as a complex function. So this f is also an element in the set of complex numbers in 0, 1 on the unit cube of dimension d. And if we now assume that we have this specific function here for neural network, the theorem goes as follows. So, and this follows Sybenko back in 1989. Sybenko, 1989. And then there's a modification by Hornig in 91. And the theorem goes as follows. So let sigma be any continuous function, continuous sigmoidal function. So it's like a sigmoid function. We're coming back to that one later today. So be any sigmoidal type of function. So as I said, I'm not proving the theorem, I'm just showing the theorem. And we are going to look at this function in the limits sigma z, where we now have a function which approaches 1 as z goes to plus infinity, and 0 as the argument c goes to minus infinity. And if you look at the plot of the sigmoidal function, or the sigmoid function, if we plot this around 0 here, and then we have as an argument z and sigma z here, what you typically would see is that the function now goes to 0 in the limit of z goes to minus infinity, and here we would have the value 1, and it goes to 1 in the limit of z goes to infinity. Now, we are coming back to some of the problems which this can lead to when we are looking at the backpropagation algorithm, because this property means that the derivative is going to be 0 when z goes to infinity or minus infinity, and that can cause problems with the training. Now, so then, given a function f, which is now an element in the unit cube of d dimensions, and a number epsilon, which is larger than 0, then there is, and this is what the theorem says, there is a one layer neural network, NN, which we're going to call F, with argument X, and with the parameters given by this collective container theta of the form so where we now have a W, which is a matrix which contains the weights of M times N. And so these are the parameters theta, and B, which is now a vector of length N. So we would have M inputs and N nodes in the hidden layer, for which so these are the parameters theta. So these theta here are the parameters which now contain a weight matrix and a bias vector, and for which we have now an approximation f of x given these parameters theta. So theta, as I said, is a collective container for the weight variables and the biases. And then minus f of x, which is the function we want to reproduce, less than this value epsilon for any or for all x, which are elements between 0 and 1 in this unit cube. And that means that any continuous function, f of x, uppercase f of x, which is supported on the unit cube, can then be approximated by a one-layer sigmoidal network to arbitrary accuracy. Now, what Hornig did back in 1991 was to extend the theorem by letting any non-constant and activation function to be included. So that means that you can have activation functions which are actually non-constant of any type, like this ReLO function or this ELO function. So Hornig actually modified this to include activation functions. So Hornig improved actually the theorem, extended the theorem to apply to any non-constant and bounded, non-constant bounded activation function. Activation function. So this plays a very important role in neural networks. And if we now go back to the setup of a neural network as we discussed last time, so let's quickly remind ourselves about that by looking at the basics of a neural network, or the basic setup of an NN. So what we had, as we discussed last time, we had something which we call the feed-forward stage. And let's now rewrite that. And in the feed-forward stage, what we had is an input layer with a given number of input nodes. As we mentioned last time, a typical example could be an image, which we are feeding in. And if the image has just one color, there's one color channel. And if it has 100 times 100 pixels, that means that we would have 10,000 input nodes. So, but we are going to write this in a slightly more schematic way here. So the input layer simply now defined in this graphical mode in terms of this inputs X. Now, this goes now in to the first hidden layer, which we are going to label with an H1. And this is now connected with the input nodes with these weights. There's a W1 here. So W with a superscript 1 to indicate that this is the connection between the input layer and the first hidden layer. So this will be the sets of hidden layers. And they're obviously called hidden because we never see these as outputs. So these are just intermediate stages in the calculations. And then we would have a set of nodes here. And we're just going to mark that with different dots. And then we had a specific node here, which we labeled with a J. So this receives an input, which we last time called set J of 1. So this is for the first hidden layer. And that was given by the weights, W1, multiplied with the inputs, X, plus these biases, which are unknown parameters for the first hidden layer. Now this produces an output, which is now modulated by the activation function we have. So there's going to be a sigma here, which takes as an argument set G of 1, and that produces an output, which we last time labeled as an AJ of 1 here, to indicate that this is the output from node J in the first hidden layer. Now, this then is fed on to the next hidden layers, and it just continues like this till we reach the next hidden layer. So let's just write that one as an H2 here. This has new biases which are fed in here, a B of 2. So this has also biases which are fed into each node. Each node has its own bias. This receives now a new matrix, which connects the hidden nodes in the previous layer with the hidden nodes in the second layer. This produces now a new output, which is given by set G of, no, not set sigma J, but Zj. And then this is an argument for the second layer that produces an AJ2. And this goes all the way to the final output layer. So then we reach the final output. And the output is something which I will just write like this in a vector form. So that has an A of L. And this is now a vector which now loops over all the nodes in the output layer. So if you just have one output, where if you're doing a typical classification problem where you want a function value with X values as input, then you would typically have one output which you would train against, true, false, for instance. If you have a classification problem with more classes, suppose now you want to classify diagnosis for patients coming into the emergency room, you could have a list of something like 20 different types of illnesses which a patient can have. So that could be a classification problem. Or you could look at handwritten numbers, which is a famous data set, which is called the MNIST data set. And you will have handwritten numbers with a given resolution. And then you have 10 numbers from 0 to 9. Then you want to recognize these numbers. Now, this output here is then the last layer. And this is fed into the cost function, C. And that cost function receives the data which we want to reproduce. And what we did last time was to label this data with T for target. So we're going to use this T as a variable here. And this is the feed-forward stage. We would typically initialize the different weights and biases. And then we would then have the next stage, which is the back propagation stage. And this is where we perform the training of the weights and the biases. So in principle, what we would have now is an output. If we look at the final output layer, this produces an output in vectorized form. Final output layer has now an output, which we are going to call an A, an L for the final layer. And this will depend on the inputs and then on all the parameters theta. And these parameters theta, which we have now, this becomes a collective container for the weights and biases of the first hidden layer, B1. Then we have the weights and the biases for the second hidden layer, and so on, till our final output layer, which in this case would now be a WL, and then we have a B of L. So this is the final output, which we now want to compare with the target values. So we would then have a cost function as a function of all these parameter theta. And if we now think of the mean squared error as a cost function, what we would have then would be 1 divided by n, and then we have the norm 2 squared of the t minus, and then we have this output from the last layer, which we also call the output layer, of x as a function of all these parameters theta. And we have the norm 2 of that, and this is squared. So this is a typical cost function. We could have other types of cost functions if we're dealing with a classification problem. And these ALs, which we have, they're actually going to be given by, so it is A of L of for the final layer as a function of the input and all the parameters. This is now given by the activation from the last hidden layer, and that receives as an input the output from the layer before, L minus 1, and which again receives the output from the layer before that, L minus 2. And this goes all the way down to the first layer. So we can write this as a sigma 1, where we now have plugged in x multiplied with the first set of weights and biases, P of 1 here. And this now contains a series of parentheses here. So what we have now is, in principle, something which we're going to translate into matrix and matrix vector multiplications. And every layer produces an in and output, which is then fed into the next layer. And this gives rise to the nonlinearity. And we calculate these outputs from every hidden node in terms of a specific activation function. So in traditional machine learning, you would actually end up playing around with different types of activation functions. So what we're going to deal with now is actually the back propagation algorithm. So let's set that up, because this is the way by which we are going to train the weights and the biases. This is nothing but an application of the chain rule, but where we start with the output instead of starting with the input. And the reason why we start with the output is that normally the dimensionality of the output matrix or vector is much, much smaller than the input. You could think of you starting with a classification of images like this set of handwritten numbers. So in this specific case, you would have 10 output categories, which would be the numbers from 0 to 9. So your output layer would then contain 10 nodes. However, the input layer would contain a number of nodes which is specified by the quality of the image. So if you're using 100 times 100 pixels and you have just one color, that gives you 10,000 input nodes. So when one of the reasons why we start with a back propagation algorithm will become clearer when we understand what's called reverse mode in the automatic differentiation algorithm, which we are coming back to after we have derived this algorithm. And then you will see much more clearly the link between automatic differentiation and the back propagation algorithm. So the back propagation algorithm is nothing but an explicit application of the chain rule. So then you will train, and going back to the input layer, you will find new values for the different parameters, the weights and the biases. When you have that, you perform a new feed-forwards pass, and then you produce a new final output, which you compare with the targets. And then you can do a new retraining with the back propagation, and then you go back and forth. So every iteration contains a feed-forward stage and a back-forward stage and a back-going stage. That is one iteration. And then you would continue with that till the cost function, which we have defined here, doesn't change by more than a parameter which you have chosen. So suppose now that you get a cost function which produces a mean square error of 10 to the minus 3, and you're happy with that, then you would typically stop the calculation. Or you would just stop when the cost function flattens out and you don't see a further change in the cost function, or any other type of variable which you're calculating. Now, before we move on to the back propagation algorithm, I just wanted to say something about problems which we can face when we are dealing with neural networks. And one of these problems is actually related to the exploding or vanishing gradients. So before we do the back propagation algorithm, which is the next step here, we are going to look first at the specific problems, and that is a problem with the vanishing gradient, problems with. So the back propagation algorithm gives you the analytical expressions for the gradients, which are needed in order to train a network. And when you're training the network, the thing you want to avoid now is that the gradients vanish or that the gradients explode. In both cases, your network will stop training. One, because you get not a number, and another case because you simply get zeros. So when you do this back and forth here, if you look at the schematic image of a network, You would then, in a feed forward stage, you would feed in the input. You have some randomly initialized weights and biases all over. And then you go through the network and end with a specific output when you're done the training. This output is compared with the targets here. Then you start calculating the gradients here, and then you go backward till you reach the first hidden layer. Then you have updated with the expressions for the gradients, and that is where you would also use things like adaptive gradient or ADAM, or you would use RMS prop to tune the learning rate. When you then have reached and obtained new values here, then you would perform a new feed forward pass till you reach the output layer. You produce a new output, compare with the targets, and then you go back and forth till this cost function, which you see here, stabilizes around a specific value. So that's essentially the training process. So we can have vanishing or exploding gradients. And I'm going to show you how this can happen. So if you now think of a very simple neural network, so just consider a simple network with two layers, a simple NN, just to get a basic understanding of what this means, in which, and we simplify this further, in which X, W, and B, the bias, are all scalars, and real numbers and reals. So we have two layers, L is equal to 2 then. So that means that the function which we produce, this is the output, is now going to be given by the activation function in the second layer, which then depends on the weights in the second layer. And then this is multiplied by the output from the previous layer, which then in turn depends on W1 times X, the input, plus a B1. And remember now that all the quantities are scalars. So this contains then a bias B2 here. Now in the real calculation, we will need then various partial derivatives as functions of matrices and vectors. But in this case, it's pretty simple. So if we now look at the derivative of this function f with respect to W1, so I'm just going to write this in a somewhat sloppy way. So this is the derivative with respect to X and take with respect to W1. This becomes equal to a sigma if we just use the standard rules for derivatives. So we have the derivative of the activation function in the final layer. And this is now going to contain W2 times sigma 1 of W1 times X plus B1 plus this B2 here. And this is multiplied with W2 multiplied with sigma 1 derivative. So we're now calculating the derivative with respect to W1. I'm just using the standard rules for derivation here of W1 of X plus B1 times X. And with L layers, if we now have more than just two layers, what we end up with then is the following equation, and it's pretty straightforward to see that. So we would then get, by generalizing this simple case with two layers, we would have the product L equal 2 up to the final layer. We would then have the weights WL, and this is multiplied with the product of all the derivatives L up to L, and then we have a sigma, and this is a sigma of L, and this takes an argument Z of L, and this is multiplied at the end with X here. And this function here, this Z of L, this argument, is actually given by now the output from a given layer L, which then contains the sigma, the inputs from the previous layers, and that takes an output from the layer before. And this goes all the way down to the first layer, sigma 1. So this is just a very schematic. So A1x is just a function which comes in as an input, this function z, which comes in as an input to the specific node in a given layer. And this contains all these activation functions which have been used to calculate this quantity here. So the thing now which we see is that if this sigma of L is a sigmoid function, or you can also look at the tan H function, you would get much the same behavior. Then what we have then, we take the derivative of sigma L as a function of z of L will be small because this function goes to roughly to a constant, either 1 or 0, when sigma L, the absolute value, goes to infinity. So this will be small when this input parameter, z of L, is much, much larger than 0. So if these quantities are small, we will typically multiply them together, making the product of them even smaller. And that means that we end up with a potential problem, which is called vanishing derivatives. And you can now see that if you go back to the shape of the sigmoid function, let me just remind you quickly of what that one looks like. So the sigmoid function has a shape which looks like this. And you see now that when z, the argument, becomes very large, and you will see the same for the tan H function. When that becomes pretty large, then the function just flattens out. And that means that its derivative is getting closer and closer to 0. Now, in that specific case, what happens is that you will have gradients which will vanish, because the gradients, as we will see now, they will depend on the derivative of the activation function. And that leads to what's called the vanishing gradient problem. We can have other cases where the gradients can become very large. And in that specific case, you will see then that we are multiplying here larger and larger numbers with each other. And that can lead to a problem of exploding gradients. Now, if we have exploding gradients, what happens then is often that we could use a technique which is called cutoff, which means that we set the gradient back to a smaller value if it goes larger than a specific value. Now, for the vanishing gradient problem, this was a problem which actually halted the developments in deep learning quite a lot. After the first initial wave of enthusiasm in the 90s, there was a paper, famous paper in 2010 by Ben Zhou and collaborators, the same author of the famous textbook on deep learning, where they showed that the sigmoid function is a function which can actually lead to these vanishing gradients. And that led people to consider other types of activation functions, as we discussed last week, like this rectified linear unit, the exponential linear units, and other types of activation functions. But this is a very delicate issue. And this means that when you are setting up a neural network and you're running the code, you would typically try out different types of activation functions. Now, this was just a small intermediate step, just to make you aware of the type of problems which we have. But now we are going to derive the backpropagation algorithm. So let's now look at the derivation and set up the quantities which we need of the backpropagation algorithm. I'm just writing it like a backprop algo. This algorithm is going to give us the analytical expression for the gradients. And with the gradients, we would typically then use some gradient descent method with an optimizer for the learning rate in order to find the optimal update of the unknown parameters. So the backpropagation algorithm is nothing but a way to provide you with analytical expressions for the gradients. Then with the gradients, you need to use a gradient optimization in order to find the parameters. So this is a two-step process. One, it provides analytical expressions. And it's going to provide analytical expressions for the gradients of the cost function as a function of the weights in a given layer and the biases of dB for a specific layer L. Now, with that, then we can update the gradients. No, sorry, not the gradients, but the weights and the biases. So we would then have a weight WL, which is now updated with a previous value of W weights at the given layer minus a learning rate, which can be dependent on the layer, multiplied with the derivatives here of delta W of L. And then we would have a same equation for the biases, and they are being updated from the previous value minus a learning rate of L multiplied with the gradients. So this is the gradient optimization part. Sorry, this is derivative with respect to B here. So I just wanted to be clear about what the backpropagation algorithm is. So the backpropagation algorithm does not update the weights and the biases, but it gives you the analytical expressions. So this is the backpropagation algorithm. So let's find these analytical expressions. And this is something which we're going to do after the break here. So I wanted to remind you a little bit of the structure of the neural network, and also tell you a little about the kind of problems we have and why many people have motivated the usage of other activation functions, because we can risk of having either exploding or vanishing gradients. And in our case, what we will be doing after the break is to set up this backpropagation algorithm. We're going to find the different parameters by using gradient optimization. And with that, hopefully, we get, for instance, a mean square error, which is small. Next week, we are also going to build our own neural network. But this week here, we are now going to derive the backpropagation algorithm, the basic mathematics, and then we are going to link that with the reverse mode in automatic differentiation, just to motivate why we do the backpropagation stage. But now it's time to take a small break and stretch legs a little bit. So the aim now is to go through step by step the derivation of the backpropagation algorithm. And next week, we are going to look at how we can implement that one numerically. And but the topic today is more to look at the backpropagation algorithm itself. So we are going back to the whiteboard again. And we will slowly go through the basic, or step by step, go through the basic elements in the algorithm. So we need to define, again, some of the quantities which we set up last time. So we have the input to a specific node in a given layer, input to node J in layer L. Let's put it like this. So we're just I'm gonna drop this parenthesis in the superscript. So this is just the input, and that will depend on the number of nodes which I have in the layer before. So this n L minus 1 is just simply the number of outputs which I had from the number of nodes in a previous layer. And then I have a weight, which is now going to depend on J and I. And this will be the weight matrix, which connects the nodes I in the previous layer with a node J in the new layer. And this is then multiplied with the output from a node I in layer L minus 1. And then in addition, I do have a bias for the node J in layer L. So this quantity which you see here, in case this is the first hidden layer, this will be nothing that the input, which we label as X. So the first hidden layer connects you with the input layer, and then obviously the final output layer connects you with the target values which we want to reproduce. And then this quantity A of I of L minus 1, that's going to be given by the activation function, which could be a sigmoid or any other type of activation functions. So I'm going to use the sigma just to label a generic activation function of L minus 1. Now, what we are going to need now are derivatives. And what I'm setting up now is some intermediate calculations which we are going to need. So if you look at the expression for Z, if I take the derivative of that input to a specific hidden node, then as a derivative with respect to the weights, let's say IJL here, if we now look at the expression which we have, this expression here, we see that this one becomes equal to AI of L minus 1. Similarly, I need another quantity to help me in the calculations now. So if I take ZG with respect to the values of the previous output layer from a given node I, then this is nothing but Wij from layer L. So these are just quantities which I'm going to need now. Another quantity which I will need is a derivative of this A of J, for a specific node, as a function of the input, because one of the reasons why I'm going to bring in all these quantities is that I'm going to use the chain rule. And when I use the chain rule, these are just going to be intermediate steps in order to derive the full equations. So this quantity here depends on how we have defined the activation function. So in this case, we could assume that this activation function is given by the sigmoid function. So let's assume now that this Aj of L, which is given by sigma for this specific layer as a function of the input to that specific node, is equal to 1 over 1 plus E of minus ZJL. So this is just a sigmoid function. So if I calculate the derivative of that one, what I'm going to get then is the following. And this is for the sigmoid function. This is going to be given by C of JL of 1 minus sigma of CJL. And we know that this is the same as the output from that specific node. So this is AJL of 1 minus AJL. So this is specific to the sigmoid function as an activation function. If we have other types of activation functions, we will get different expressions for that. Now, a thing which is important from a computational point of view, so if we look at that as a computational note here, so if you look at that specific derivative, is that these derivatives, I mean the last ones, these derivatives will change when we change activation functions. So when you're writing a code for a neural network, it can be convenient then to actually make a class of activation functions and then simply define these derivatives in terms of the specific activation function which we have opted for. Now, what we are going to start with, however, since we want to do the backpropagation, is that we are going to start with the output values. So if we go back a little bit now, and if we look at the backpropagation algorithm and the graph of a neural network, we just scroll a little bit back here, what we're going to do now is to calculate the derivative of the cost function, because this is, after all, the quantity which we want to minimize. So that means that we are going to calculate the derivative of this cost function as a function of the weights and the biases in the output layer. And we're going to use that as a way to calculate the other derivatives of, and that means leading to gradients for the weights and the biases as we move back in the network. But we are going to start with the outputs, which we have here, this A of L. and we're going to compare that with the targets using the cost function. And we're going to take the derivative of the cost function with respect to the parameters. So what we are going to assume now is that we have this mean squared error as an example. So example cost function. And if we have another cost function, we would have to change the derivatives here. But in general, we can make the code so general that we can change between classification problems, regression problems with different types of activation functions. And we will see that when we are starting to look at the codes next week. So example of C of theta. So this is so let's just put it down here, and I'm going to drop the 1 over n factor. I'm going to put a factor of 1 over half, which is pretty common, because then we can simply now, when we take the derivative, we will get rid of the factor of 2 from the squared term, which we have for the cost function here. So what we are going to have is a output A of L. L, the uppercase letter L, stands now for the output layer, minus T of I, which is the target we want to reproduce, squared. And you see now that when we take the derivative, we are going to get rid of the term 2 because we have a factor of 1/2 in front of it. So what we will need now is the following. So we will need dc of theta as a function of the weights of jk, a given random pair of a pair of columns and rows which contain a specific weight for the output layer L. And we are going to need the derivative of the same quantity for the bias in the specific layer, which now is the output layer. So if we now look at the expression which we put up here, so what we would have is that d of c of d, and I'm skipping these theta parameters, of j of k of L is obviously now, when we use the chain rule, we get rid of the factor of 1/2. So we get simply an A of j of L. So we are looking at the derivative of this expression here, minus T of I. And this is obviously multiplied with the derivative of the output from layer L, the output layer, for node J. And this is now given by del of jk of L. Now, so we pick this specific node J, and when we look at the chain rule here, if we use that one, so the chain rule is now going to give us that this d of aj of L. Please don't hesitate to ask if something is unclear. If we now use the chain rule, we can always rewrite that in terms of aj, and now you will see why we need this intermediate steps which we discussed previously. So we need this one of dz of wj of k of L, because aj depends on the input, which then in turn depends on the weights. And if you now look at what we had previously, so if you look at this term here is something which we have defined here. If we now use the sigmoid function, and then if we now look at the second term, this one is nothing but the term which we put in up here. So we have a term here, and we have a term here, which we can now use. So this is a term which we will need, and we see that that depends on the output from the previous layer. So if we do that, if we insert this and we use the sigmoid function for the activation function, so then what we would get with sigmoid for this function z, sigma z of z, what we get then is that this quantity daj of L of d omega jk of the unknown weights is now going to be given by the output j multiplied with 1 minus ajl. This quantity which you see here is nothing but the derivative of the activation function. So we would write this as a dz here. And then what we have next is obviously ak of L minus 1, when we use the expression which we have here for dz with respect to the weights. So if I now go back to my function, what I have is that dc, the cost function, the derivative of it at the output layer, is now given by my aj of L minus the target tj multiplied with aj of L, 1 minus aj of L, and this is multiplied with ak of L minus 1, the previous layer. And we could rewrite this in terms of aj L minus tj, and this is multiplied with the derivative of the activation function of cjl and multiplied with ak of L minus 1. And you see now why I mentioned this computational note a little bit earlier here. So what we could do now is simply, if we have another activation function, the only thing we need to pay attention to is the derivative of the different activation functions. So if we change activation function to real, for instance, we would need to plug in another type of derivative. But this is just something which becomes a technicality which we will study next week. Now we have this kind of derivative, and it's common to actually encompass several of these constants in terms of just one. So if we now go back and look at this specific expression which we have here, so this expression here, it is common to actually relabel parts of it in terms of a specific constant. So what we would have then is that we're going to define a constant delta j of L, which is going to be given by aj of L minus tj. Sorry, aj of L, not that one. That was not the one I wanted. So we have an aj of L multiplied with 1 minus aj of L times aj of L minus tj. And this constant here is nothing but the derivative of the activation function, set j of L, and this is multiplied with the derivative of the cost function with respect to this aj of L. So this is just a constant which we need now. And if you now see what we have done here, what we have is that we have simply replaced these terms here with just this constant. And then we simply need to multiply with that constant, which is the output from the previous layer. So if we now collect everything, what we would have is an expression for dc with respect to the weights in the output layer. And this is given by this constant delta j of L multiplied with the output from node k in the previous layer. So this is the first equation which we would need to use in order to calculate the gradients. That's step one. Now, another thing you can observe very easily, so I leave that as an exercise to you guys, so we can easily see that this delta j of L is actually the same as dc of dzj of L, which is again the same as dc of d of aj of L and multiply with daj. So I'm going to leave some of these derivations as a small exercise to you folks. And then similarly, we can show that this delta j of L is actually going to be equal to the derivative with respect to the biases. If we now just use the chain rule of dc of the dc of jl, and this is the same as d of c, and you can easily see that one because when we take the derivative of this dc with respect to bj, we're just going to get 1. So we are left with simply this expression here. So this term here, when you go back to the definition, this term here is actually equal to 1. So what we have now are the expressions for the derivatives. So what we can do, if we now collect everything, collect for L layer equal to the output layer, we will now have three equations, and we're just going to miss one equation here. So we have a delta C of W J K L, which is now going to be given by this expression here in terms of this constant of AKL minus 1. We have that this term JL, delta JL, is going to be given by the derivative of the activation function with a specific argument, and this is multiplied with the derivative, partial derivative of the cost function with respect to the output from the network. And then we also have delta JL equal to dC of Bj of L. So these are the three first equations which we need to actually set up. So we do everything for the output layer, and then we have the gradients for the different quantities. And with the different gradients, we can now update the parameters B and the parameters Wj in the training. Now, what we're going to do next now is actually to look at L goes over to a given layer, which is not the hidden layer, no, the output layer, where this one is actually different from L. So that means that we need now to set up an expression for this delta J of L. This is going to be an important expression. And we are going to put that one up in terms of set J of L. And we show that this is actually equivalent to that term. And the thing we do now is that we simply use the chain rule again, and we sum up over the inputs from the previous layer, so K of L plus 1, and then we have a C of L plus 1 with respect to dZj of L. So what I did here was simply just to implement the chain rule, and this will become much clearer when we look at the reverse mode in the back in automatic differentiation. So this, we can rewrite this, and we know what this actually is. The first term is something which we can replace with the function delta. So we can rewrite this one as a delta of K of L plus 1. And this is multiplied with the partial derivative of the input from layer L plus 1 with respect to the input on node J from layer L. Now, if we now look at the expression for dJ of L plus 1, this is what we defined a little bit earlier. This is the same as I equal 1 up to NL, the number of nodes we have in the previous layer. There is going to be a weight element of L plus 1 multiplied with the output from the previous layer, node I, plus the bias, Bj of L plus 1. So then you see immediately that if I take the derivative, the partial derivative of K of L plus 1 with respect to set J of L, then this is going to be Wk of J of L plus 1. And then I take the derivative of, I have to take the derivative of this quantity, which is actually nothing but the derivative of the output from the function which we have. And in our case, this is going to be the activation function. So this is going to be sigma of ZJL. Because we know that this quantity which we have here, this is nothing but Z of CJL here, sigma of CJL. And that means that when I take the derivative here with respect to CJL, since the weights don't have a dependence on that, then we are simply left with the derivative of the output, which is the same as the derivative of the activation function. So this is again a piece which we can keep general. If we have defined different types of activation functions, we can reutilize the same code, but just changing the activation functions. So when we now collect everything, what we have is the final expression, delta J of L, and then we are ready to go. So that's going to have be represented by a sum over delta K of L plus 1. I'm going to have the weights in the layer here, L plus 1, and this is going to be multiplied with the activation function and its derivatives with respect to set JL. So this is essentially the 4 equations which are needed in order to set up the expression for the gradients. So this is the final expression here. And when we now are setting up the final algorithm for the neural network, then what we will do then is the following. So we have a final algorithm. So the final algorithm starts with an initialization, initialize weights and biases, and we just write this as a theta, which now is going to be a collective container for the weights and the biases for all the layers which we have. The next step is to perform the first feed-forward pass. Feed-forward pass. Then we produce an output. So this A of I of L is used in the cost function to compute the cost function C of theta, and we compare that with the gradients. No, sorry, with the targets. Then we perform the back propagation step. Perform back propagation. And in that case, we have now the expression for the gradients with the back propagation algorithm. And this stage goes as follows. So for each stage, L equal L minus 1, L minus 2, and down to the first hidden layer, which is labeled as 2 here, because the first layer is actually the input layer. Then in each case, we would now calculate this delta J of L, which is simply given by the sum of K, of delta K, of L plus 1, the weights, which we had from the feed-forward pass. These are just the initial weights, multiplied with the derivative of the activation function. Then, when we have that quantity, we know that these are the gradients, and we know that this is part of the gradients, and we know then that we can update the weights with the previous value, J of K of L minus, and now we have a eta parameter, which is the learning rate. So let me just emphasize that one, because that becomes a parameter we would now tune with the same methods which we are using in project number 1. And we would typically set this calculation up with a gradient descent or stochastic gradient descent, and then we can have tunable learning rates which change iteration by iteration. So this would now contain a delta J of L multiplied with this AK of L minus 1. That's for the weights. And then we have a similar expression for the biases. So the biases would be a B of J of L being updated from the previous value minus eta times dC of dBJL. And this last quantity is something which we can rewrite in terms of a BJL, the previous value, minus eta, and this is multiplied with delta JL. So having this quantity delta JL is actually essential in the calculations because it comes up here and it comes up here again. And this is a back propagation algorithm which allows us to update the weights and biases. So this gamma, this eta parameter is nothing but the learning rate. And here we have to decide upon an algorithm for calculating the learning rate. So we can have a fixed learning rate, or we can have an adaptive learning rate, as is the task for the first project. So this is an end for. So we end the loop. And then when we have performed the first backpropagation step, what we would do next then is just to go back to the feed forward stage here. We compute now the new outputs and compare that with the targets in the cost function. And then we perform the backpropagation stage again. And we keep going till the cost function now reaches a constant value. So what we will do next is this final stage, repeat the steps 1 to 4 till this function c of theta stabilizes or converges to a specific value. It doesn't change anymore, stabilizes. And then we would output the parameters theta, which are now the weights and the biases. And this is our description of the function which we want to optimize, which in turn, which gives us the optimal description of the function of this function which we called f of x, which we assume is a deterministic function and which exists. So that's the basic algorithms which we need to implement now. But before we look at the actual implementation, it's actually useful to take a look at the so-called automatic differentiation algorithm. So let's look a little bit about what automatic differentiation is doing now as we have the backpropagation algorithm. And you can actually look at this backpropagation algorithm now as the product of a whole chain of partial derivatives. So let us see why the automatic differentiation and the backpropagation can be linked together. So automatic differentiation nowadays is actually implemented via a library called AutoGrad, or even better, you have JAX now, which also include highly vectorized code. So JAX has replaced the older version of AutoGrad. Replaces if you're using Python, AutoGrad. And we saw examples of using AutoGrad and JAX before we had the break, when we were now looking at just the calculations of the gradients for the adaptive gradient algorithm, AdaGrad, or root mean square propagation, RMS-prop, or the ADAM algorithm, which is adaptive learning rate with momentum. So let's now take a look at some functions here. And let's just look at an example and try to motivate this with examples. We will continue with this topic next week as well. So let's take a simple example as a function f of x, which is just given by the exponential of x squared. So we know that the derivative here is actually pretty simple to calculate. So we would now calculate the derivative of this function with respect to x, which is just equal to 2x times the exponential of x squared. That's pretty easy. So the kind of approach which we are going to use is now the following. So we're going to define some intermediate steps, and we will define now function a, which is given by x squared. And then we are going to define a function b, which is going to be the exponential of a, and this is going to be the same as f of x. So f of x is equal to b, okay? Graphically, we can represent this in the following way, and this gives us a kind of link between what we do with neural networks and automatic differentiation. So this goes in to the definition of the function a, which is our x squared, and this goes into the definition of the function b, which is the same as the exponential of x squared. And this finally gives us the function f here. Now, if I want to calculate the derivative here, so if I want df dx, I can write this out by starting with a derivative of f with respect to b, multiplied with the derivative with respect to a, and this is given finally by dA dx here. So if you now look at the first term which we have here, this one, if you now look at the definitions which we have, it's pretty easy to see that this df dB has to be equal to 1. Would you agree with that? Does that sound reasonable? So in our specific case, this is actually equal to 1. Now, starting with the calculation here, and that's why I'm marking this with red, this is actually called the reverse mode. So we start with the calculation of the derivative of the output of the function f. We feed in an x, and then we have a final function f. So we are starting the process of derivation by actually looking at the derivative of f with respect to this function b. So this reminds us a little bit of what we are doing with back propagation, but we don't have the connection fully yet. So when we do this, this specific way of calculating the derivatives would then be called the reverse mode. And then we would go from the derivative with f of f with respect to b, and then we take b with respect to a, and finally we would have a with respect to x. Now, the other type of mode which we have is another one where we could actually rewrite this as a df dB, but then we focus on the calculation of dB dA and dA dx. So the terms which are marked in the brackets here, these are the terms which we evaluate first. So this is normally called a forward mode, because we don't start with the derivative of the last quantity in this graph here. So this is a typical example of the difference between a reverse mode and a forward mode. Now here, we do not appreciate properly what it actually means. So let's look at the new example. So let's take that, new example. And in this case, I'm going to look at a slightly more complicated function, because then it becomes useful to also see where the benefit comes with the specific usage of the chain rule, which we have when we do automatic differentiation. Now, in this case, what we have is a new set of functions which we can define. So we would have a is equal to x squared. We can define a new function, which is b, which is the exponential of a. Then we would have a new function, which I'm going to call c, which is a plus b. And finally, I have a new function d, which is going to be the square root of c, and that is the same as f of x. Now, if we now calculate the derivative, on the other hand, what we get is the following: d of f of d of x is now going to be equal to x times 1 plus the exponential here of x squared. And this is divided by x squared plus the exponential with x squared as argument here. Does that sound reasonable? So if we now look at it, what we have is a function which we can rewrite in terms of these quantities which we have defined. So we would have x of 1 plus b, and then divided by the square root of a plus b, which again is the same as x multiplied with 1 plus d divided by the square root of c, which in turn is equal to x of 1 plus b divided by the square root, by the quantity d here. So the expression which we have now is a much more compact expression. And one of the things which I'm going to invite you to take a look at is actually the number of floating point operations, which you get by this type of calculation. So we're coming back to that next week, because then you will see that when we do the back propagation, we can, depending on the type of function, we can actually reduce the number of floating point operations when we use automatic differentiation in reverse mode contra forward mode. Let's now look at the graphical representation of this specific function. So we would now write this one graphically in the following way. What we would have then would be x, and x feeds into this function a, which we have defined previously. And this now has an intermediate step. So we're going to just put a plus here. So we have this a, and which is x squared. And if you now look at the function which we have, so we have an x squared plus exp x squared. So we are going to label this graphically with an intermediate step here where we calculate the function b. So this is x squared. And now we have the function b here, which is exp of x squared. And this goes down into this one with an addition. So we have a plus b. Now this feeds into c. So we calculate a plus b as an intermediate stage, as you can see here. Then we have the stage d, which is actually the square root operation, and that gives us the final expression. So we then have d here, where we now have performed the square root operation, and this goes over to the final function f, which we are outputting here. So in this case, f of x is actually equal to d here. Now let's now set up the derivatives. So we have a dA of d of x, which is the same as 2 times x. We have dB with respect to x, which is the same as dB of the partial derivative with respect to a, and then the partial derivative of a with respect to x. Because remember now that b depends on x and a. So we have defined a to be x squared. So that means that when we take dB dx, it has to have, using the chain rule, it has to take the derivative of b with respect to a. Then the next term which we need is a dc dx, which is now going to be given by dc of d of a, of dA d of x, plus a dc of dB of dB of d of x. Then we know that this specific quantity which we have here actually can be simplified, but let's continue a little bit now. So we would then have a d of d with respect to c, which is 1 divided by 2 times square root of c. And finally, I have my d of d of x, which now becomes equal to d of dc of dc of d of x, obviously, because I now have, as you can see here, I have the expression for this quantity. And you see also that my dB dx, this quantity, can then enters in here. So we then have this quantity to be placed instead of that one. So in this term here, I didn't write out the final expression which I'm going to use because my dB dx is given in terms of dB dA and dA dx here. So this would be my final function here. And since d is equal to f, if we now go back to the definition which we put, so we have d is equal to f of x here, then this quantity here is the same as df of d of x. So this would be something which we now could use in order to calculate everything in the forward mode. So if we now look at the computation in reverse mode, so we would end up at the very end, after we've gone through all these calculations, we start with a dA dx, we calculate dB dx, we do dC dx, dD dx, and then finally, this is the same as dF dx. Then we have performed the forward mode stage of the automatic differentiation. But let's now look at the computation in reverse mode. In that specific case, and I see that my time is unfortunately running out, so we are going to look at this part here next time. This is where we will start next time. And we are going to link what you see here with the backpropagation algorithm, because they are going to be equivalent. This is actually something which is under-communicated in machine learning. And then we're going to look at some consequences of why this reverse mode is so interesting and why it's so useful to use automatic differentiation when we are dealing with the deep learning methods. So I'm just writing here more next week. I see my time is over, and we are going to look at the final details here. Next week, we're going to look at the number of floating point operations which we get, and then we're going to try to visualize and argue why this would be the same as setting up the backpropagation algorithm. I'm going to stop the recording here now.